Welcome. Let's unveil the deepest, darkest secrets of calculus and its application. We're going to be making a whole series on this topic and we're going to be covering limits, derivatives, integrals, and a lot more. It's not a mathematician's point of view, but a physicist one. We're going to mathematicians get out of here because we're going to be treating derivatives like fractions. So let's start with the basic understandings. You don't need that much mathematical prerequisites to understand calculus, just some basic algebra. Our first topic, which is a function. Functions are nothing but some machines. Suppose you have a machine here, let's call it M, and in this machine you give input to, let's say, wheat, sugar, water, and a lot more. What this machine gives you as input is cookies. Nice looking cookies. This machine, in the context of mathematics, is called as a function. This is, we're going to be simply calling it inputs, and it's just the output. A function is usually defined as f of x. X is here an input, and this f of x is the f is here the whole machine, and f of x is the total input. And this machine always needs an instruction. In mathematics context, this could be like x squared or 2x or even quadratic x squared plus 5x minus 6, whatever. This is all about functions. We're not going to be delving deeper into it, but some basic ideas. We're not going to be solving problems, but understand what they all mean. Our next topic, let's give an example. Let's say f of x is given by x squared minus 9x minus 3. And we want to find what f of 3 is. F of 3 just means we're inputting x equal to 3. X equal to 3. So this is going to give us 3 squared minus 9, 3 minus 3, which is just 0 by 0 and it's undefined. This is where we're going to be looking at limits. So in limit, we don't actually put x equals to 3, we put x equals to 2.999 or x equals to 3.0001 or a value very close to our main x value. And then this equation or this output, as we say, must be a definite value, not an undefined thing. I'm not going to be computing it. I don't have the calculator now. So, but there's another way of solving it. We can just put x plus 3 times x minus 3 divided by x minus 3 as x squared minus 9 can be written as this, and cancel out this. We're going to get x plus 3. And if we put 2.999, this is like, both of them would give you like 5.999 or 6.000. Both of the values are superbly closer to 6, and this is a reduced value of this, and if we put x equals 3, this is definitely give us 6. This is limit. It's a basic case. Now we have to draw some graphs. So this we have, you may be heard of this Cartesian graph Draw it. Yeah, this is kind of correlation graph, and in this you have the x value, and this is the output of y value or f of x value, whatever you like to call it. Let's say f of x gives us 2x, and if you plot this graph, it's a 0 0.1, 2, 3, 4, 5. This is likely to give us a straight line like this. This is a straight line, and you can measure how much this curve or straight line, this straight value increases over the change of x. Now we're going to be computing it. Let's say the rate of change is the same all everywhere because it's a linear function. It doesn't have any exponentiations over 2. So when it's 2, it gives us 4. When it's 3, it gives us 6. So its change is 6 minus 4 divided by 3 minus 2, which is just 2 by 1 or 2. That's what we're seeing. For each value of x, this is doubling the value. This is doubling the value. It's the basic idea of derivatives, or what we call the slope of a straight line. Now, if we consider not that linear function, but f of x equals to x squared, how will the value change? Let's get through it. I'm going to draw another graph. Like this. This is the 0, 1, 2, 3, 4. Extend it. Now, 0 squared is just 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So our graph would likely to be like this. This is kind of the graph of x squared. But how do you find its derivative or its slope? This rate of change is not the same everywhere. If the rate of change is now changing, what can we do? We have to think about one thing. You know that if it's a circle, it's made of curved, bounded curved lines. And if we zoom in extremely small scale, this curved line would give us a straight line. This straight line. This is all what needs to find the derivative of this curve. We're not going to be thinking of this whole thing, but a very specific value. Let's take 2 as one point, this, and a very small change in 2. This point in between these two lines is definitely a straight line. This is not actually a straight line, but over exaggerating, that's a basic idea. If you say 2, it's just 2 squared. And if we take 2.00, let's say 1, this is 2.01, which would just give us 2.01 square. Or more fancy way, we can write this as f of 2 and f of 2.01. And notice, the smaller the value, the smaller the change in 2 is, or the smaller the change in x is, the more straighter the line gets. This is it. So we can write 2.01 squared minus 2 squared divided by 2.01 minus 2. Now, we can write it in a more formal way. We're not going to be only looking at 2, but we're going to be looking at the whole generalized case. We're going to get x and x squared. But here, the small change, we can just write x.001. It's not something we can write. So we're going to define a new function, which is the dx function. This d means a small change in this x. Let's say here we have x. The first thing we'll consider is 1. So dx would mean 1.0001 minus 1, or a very small change in 0.0001, I guess. Yeah. So we'll look at this x plus dx. This is a little bit off by dx. Dx tends to go to 0, but that's not 0. That tends to go to 0. So our thing would be x plus dx all squared. When we need a generalized thing, we're not going to be considering x squared but f of x. And we're not going to be writing x plus dx all squared. We're going to write f of x plus dx. Now, that small thing, as we saw there, the previous example, f of x plus dx minus f of x and x plus dx minus x. This positive x, negative x gets cancelled out, and f of x plus dx minus f of x divided by dx. This is what we call the fundamental theorem of calculus. Write it here. Minus f of x divided by dx. Now you may notice another thing, that this whole thing, this is a small off, a little bit off by f of x. So we can see that this numerator here is also a small change in the function of x. Now we can write it this way, d of f of x divided by dx. But this doesn't work for all formulas or calculating the derivative, so we're going to be using this for calculating the derivative. But that's the general idea. You may see this dy by dx, and f of x can also be written as dy. So this is the same thing. The small change in the function divided by small change in the x-axis. And the small change would be closer to 0. And this is what we call the limit. It approaches 0. If we want to use this formula, we have to consider another thing, which is the limit that dx tends to go to 0. As it goes to 0, our function doesn't really change, but it gives us a straight line, and now we can find the slope or derivative of this. Actually, we're not finding derivative of that curve, we're finding derivative of its little slope, this tangent line, which is definitely straight line, but this curve is not. Maybe that's not so clear in the video, but it's the general case. Now let me give you some examples. Consider that whole thing, that f of x is x squared. Now Now we can write f of x plus no f of dx all squared as f of x as we defined as x squared minus x squared divided by dx, and the basic algebra formula x squared plus 2x dx plus dx all squared minus x squared, and this x squared gets cancelled out. In the denominator we get dx, and this gives us 2x dx plus dx all squared divided by dx. Now we can take dx as common in the numerator, so 2x plus dx divided by dx, and this dx cancels out. We get 2x plus dx, and this dx is practically zero, not theoretically, but practically it's zero, so just ignore it. Our derivative of the function x squared is just 2x. We can write it in a more formal way, that d of x squared equals by dx is 2x. And if you do the same thing with the cubic function dx cubed dx, you should figure it out by yourself, but I'm gonna give you the answer only, which is 3x squared dx to the power 4th. This is gonna give us 4x cubed. You should figure it out by yourself, homework, but there's a pattern. You see the pattern? If we find the derivative of an exponent, a function with a linear exponent, we just get this function x squared, this 2 is getting here, and this 2 minus 1 is getting subtracted by 1. Now we're left with 2x. This is the same for this. The x cubed, this 3 comes here, and 1 gets minus out from this 3. And here in 4th power, this 4 comes here, and 4 minus 1 is just 3. This is called the power rule of differentiation. So if we want to write a more generalized formula for any power, you can say d of x to the power n divided by dx. This is going to give us n times x times to the power n minus 1. This is it. This is the power rule of differentiation. That's all for today.